cut grass biomass to measure fuels. We're very appreciative of people that would do work like this, so we don't have to be out there in the field as much, and also how this sort of applies to modeling. So take it away, Angie.
Yeah, thanks a lot, Clay. So I'm not going to talk too much about fuels today, except in the context of how they might burn under various weather scenarios. And the original title of my talk was Examining Future Fire Weather Scenarios in Hawaii. I didn't actually get any future stuff. I developed the data that I need to project into the future. Those projections just haven't been done yet. I will show you some pretty interesting stuff that compares past conditions with current conditions and talk a little bit about what those conditions might turn into in the future. So I'm going to talk today about these three concepts, and there's only two words up there. Weather, weather, and fire. And so these are three related concepts, and they all play off of one another. And the first thing I'm going to talk about is just changes in the weather from the decade of the 1950s to the decade of the 2000s. And this is a pretty good window to look at because it's a time scale on which the changes in weather are evident, but it's also a time scale on which a lot of people start to think about climate change. Okay, where are we going to be in 50 years? People don't tend to think about climate change in 5-year increments or 10-year increments, but that 50-year increment is really a big one that people look to. And when I do the future fire stuff, that's the decade that I'm going to be looking at is 2050, 2059, that sort of mid-century window. Then what I'm going to do is talk about a little bit about what the difference between weather is and fire weather, and also look at some of the changes in those things from mid-century to the first decade of this century. And then I'll talk a little bit about changes in potential fire behavior. So when we're looking at the weather from the decade of the 50s to the decade of the aughts, what are we looking for? We're looking for changes in hot and dry conditions. And so hot and dry conditions are low relative humidity, which makes the fuel moistures low. We're looking for high air temperatures. High air temperatures can also push down the relative humidity. It can push up the fuel temperature, which means that particular piece of fuel is easier to ignite. It's easier for a fire to come by and start that piece of fuel on fire and spread the fire faster. And we're also looking for changes in wind speed. We're not really sure. We have a general idea that air temperatures, because of global climate change, are going to be going up, but we're not too sure what's going to be happening with wind speeds. And so maybe those changes will be, wind speeds will increase, maybe they'll decrease. We're not really sure, but we'll look. So the first thing that I did was I got weather records from the Honolulu airport. I chose this location because it's one of the few locations that has reliable daily records back through the 50s. The records start in the, sort of the middle of 1939, but the really good stuff starts sort of in the 50s, and it gets really great around mid-60s. Anyway, you start with this huge fire record database. They give it to you as a text file. I put it in an Excel here. It's got something like 660,000 lines and a zillion columns of all kinds of stuff. And you sort of boil that down to sort of 7 or 9 variables that you really need to understand fire. And so the main ones that we're looking at are what's the temperature and what's the relative humidity at 1300 hours? So sort of that early afternoon, beginning of the peak fire time of day. What are the conditions then? Then we're also looking for what have the conditions been in the last 24-hour periods. We're looking for maximum temperature and minimum temperature, maximum and minimum relative humidity, because that gives us an idea of how the fuels in that location have been responding to the changes in those sort of ambient conditions. Has it been really dry for the past day, for the past week? If it has been, those fuels are going to be drier. They're going to burn hotter and faster. If it's been cool and wet, maybe you're at a hot day, but it's been cool and wet for the last week, and so your fuel moistures are probably going to be a little bit lower. We're also looking for precipitation. How much has it rained? How long has it rained for? We're also looking for wind speed and direction. Is it blowing really hard? Is it coming from the south, north, whatever? Then you take those records and you import them into an analysis program like this one. This is Fire Family Plus. It's pretty simple but pretty powerful. And what you can do is you can then break that data set down And you can look at individual time periods, and you can look at windows of analysis from a day to a week to a month. And so what I'm showing here on the bottom is just an example of the decade of the 2000s. We're looking at every air temperature at 1300 hours for that whole 10-year period. And you can see on the left-hand side, there's sort of like a graph of what it looks like throughout the year. And on the right side, it gives you an idea of where are sort of the extreme values. So the red line at the top, do I have a pointer? No. So the red line at the top shows you sort of the 90th percentile. So what temperature is it that's 90%, that's higher than 90% of the other observations? And in this decade, I think it's 31 degrees Celsius, so a little over 87 degrees. And so what I did was I took that analysis and I started to look back, and I wanted to compare those dry conditions, so relative humidity, and I wanted to compare maximum temperatures. Because when you compare dry conditions, or when you combine dry conditions and high temperatures, that's the time when you're going to get the most intense fire behavior. So here you can see the average monthly high for the 1950s. The light blue line is the average monthly high for all 10 months, or all 10 years, across all the 12 months of the year. And then the dark blue line is the average temperature of the hottest month in that 10-year period. So that's just the 1950s. When you compare that to the 2000s, your 2000s look quite a bit different. They're hotter. The average monthly high temperature for the 2000s is actually higher than the extreme values from the 1950s, and your extreme values from the 2000s are sort of unprecedented in your temperature record. Humidity is a little bit more variable. This is the humidity, again, the minimum relative humidity levels across 10 years for each month. And then in the 2000s, you have your driest months are significantly drier than your driest months used to be in the 1950s. But your wet months, or your average months in the 2000s, they're kind of close to your 1950s values. So the story for temperature and precipitation, at least on a monthly timescale, is, yeah, we have lots of warmer temperatures, and they're sort of all in the direction of warmer. But when it comes to relative humidity, the story is a little bit more mixed. There's definitely drier months, but some months may be, a little bit more moist. So then I also looked at daily high temperature patterns. So we looked at, for the 1950s and the 2000s, there's something like 3,652 days with 2 leap years in there. And so the high temperature this is the high temperature for every day in the 1950s and every day in the 2000s. And what you can see is there's been a shift towards an increase of high temperatures at high levels. So let me go back one. In the 1950s, you had 61 days with a high temperature of 31 C, so that's a high temperature of about 88. But in the 2000s, you had over 750 days with a high temperature of 31. That's a massive increase of 1,100%. So you're going from about 2 months of high temperatures that are about 87 degrees Fahrenheit and hotter to over 2 years worth, almost 3 years worth of high temperatures. And what's interesting is at the very bottom end and the very top end of these distributions, that's where you can see the changes most starkly. As far as low high temperatures, in the 50s, the high temperature hit 21 only once. In the 2000s, it didn't hit it at all. But at 22 degrees, in the 50s, it hit it 10 times. In the 2000s, only once. So on the right-hand side, you can see the change in the frequency in percentage terms. So you have a massive decrease in percentage of low high temperatures from the past to the present, and you have a massive increase in high temperatures from the past to the present. And so the number of days with high temperatures at or above 31 C, that's about, again, 87 degrees. In the 1950s, about 2.5 months worth. In the 2000s, about 3 years worth. So it's a pretty nonlinear increase in frequency of your hot days. The minimum relative humidity patterns are a little bit different. You have more, the data set for the 2000s is more spread out than the data set for the 1950s. In the 50s, the range of relative humidities is smaller, and the 2000s is a little bit higher. But you still have, the top red box shows you an increase in low humidities and a decrease in high humidities. So there is, the bulk of the data is saying that it's drier, but the overall shape of the data is a little bit wider. Okay, so summary of the weather changes. Small changes in average temperature over time can have large effects on the frequency of hot temperatures. So the average change in the temperature was probably about 2 degrees, but the frequency of high temperatures went up by a couple thousand%. Relative humidity, a little bit larger variation, but definitely an increase in low humidities. Okay, so moving from weather into fire weather, moving from regular weather into fire weather, I'll talk just briefly about how temperature and humidity are related to fire weather. And the way that they get translated is through the fuel moisture. So each piece of fuel out there on the landscape has some proportion, has some amount of wetness in it. How wet is that piece of fuel? You can think of it like each piece of fuel like a sponge. And the drier that sponge is, the hotter or faster it'll burn. So fuel moisture measures how wet that fuel is. And so higher temperatures and lower humidity mean a couple things for that piece of fuel and how wet it is. One, it means the fuel dries out more quickly. Two, it means the fuels ignite more quickly. And three, it means they release heat faster and or burn more quickly. And when we talk about fire weather, we're talking about those fuel moistures. We're also talking about wind speed and direction to a certain extent. And we also, the way that we sort of quantify those things and think about them in a probabilistic sense is we talk about percentiles. And so the fire weather that I'm going to show you here is based on the 90th percentile. And that means what's the value of this particular variable that's higher than 90% of the other values of that particular variable over the course of the data set. And so this is a 90th percentile fuel moisture and fire weather chart comparing the 1950s and the 2000s. On the left-hand side, you have different types of fuel. The first one is small diameter stuff, then sort of medium diameter, large diameter. That's all dead, woody stuff that's laying around on the ground. The next two are live herbaceous fuels, so like grasses and other non-woody stuff that grows on the ground. And the last one is live woody fuel, so all your shrubs and their little branches and the branches of the trees. And what you can see is that sort of 90th percentile condition has changed from the 1950s to the 2000s. You get a decrease of anywhere from 6 to 15% in your fuel moistures, which means in the 2000s, your 90th percentile, the conditions that are more extreme than 90% of the other conditions are themselves more extreme than the conditions that we had in the 1950s. And overall, it points to more widespread drying of those fuels. And I said I was going to look at wind speeds. The wind speeds didn't change very much. They're, over the course of the 2 decades, maybe a 1% change in average wind speed. I don't really know if that's significant or not. And so those fuel moistures and that fire weather gets translated into fire behavior and other fire attributes. And the kinds of things that we talk about when we're looking at fire behavior and other fire attributes are things like flame length, how tall are the flames, rate of spread, how fast is the fire spreading across the landscape, the intensity of the fire, how hot is that fire burning. Other fire attributes that are interesting, especially from a management standpoint or a firefighting standpoint, is how long is the fire perimeter? Is the fire perimeter, 20 meters? Can we get around it easily? Is it 200 meters? Is it 2 kilometers? And then, of course, the one that you hear on the news all the time is fire area. How big is it? How much area does it cover? Are we talking about hectares? Are we talking about square meters? Are we talking about square kilometers? These are things that are all sort of derived from the fire behavior itself. And so I just wanted to talk very briefly about some of the potential fire weather impacts on fire behavior when you compare the 1950s to the 2000s. The first thing that I want to say about this is these results on this page come from a standard fuel model, a standard fire behavior fuel model, and they're used to make a point. I'm not trying to make a prediction about what's happening in Hawaii at a certain location on a certain day. I'm just trying to illustrate that small changes in temperature and small changes in the frequency or large changes in the frequency of high temperatures or small changes in the absolute change in temperature can have big effects on what that potential fire behavior is. And so the first thing you can see is when you compared rate of spread from the 1950s to the 2000s, you had a tenfold increase in the rate of spread. So instead of a couple inches a minute, you're going on to a couple inches per second, you're going up to over a meter per second. Your fire line intensity, the amount of heat that fire is releasing, has increased exponentially, and your flame lengths have increased fivefold. So the fire itself, even though you're assuming that the fuel stay the same, you're assuming that the wind is blowing the same way, you're assuming that the slope is staying the same, you're not changing the landscape at all, you're only changing the fuel moisture, so you're getting an extremely large increase in potential fire behavior. Now I was going to talk a little bit more about area and perimeter, but the way that this particular model spits them out makes it sound extremely scary. You get, exponential 100 times larger fires in the 2000s than you get in the 1950s. And I don't need to scare anybody. I just want to make the point that even if we think in our brains that, oh, it's 2 degrees warmer, that can translate into an exponentially more dangerous fire situation. So the conclusions are basically just that. Changes in fire weather can have nonlinear exponential effects on fire behavior and other fire properties. And I didn't talk too much about the future stuff, but if you can imagine just 2 more additional degrees of warming, which doesn't sound like that much, again, we're going to have exponential feedbacks into potential fire behavior and fire weather. Thanks to my co-authors and co-collaborators, and Doug and Clay for organizing and stepping up, and Elizabeth Pickett. I thought you helped to organize, so I put you in, but I guess not. And that's it. I'll take some questions if there's time.